Hi there, my name is Sharbel Tok. I am a postdoctoral research fellow at the University of Wollongong, Australia, and the ARC Center of Excellence for Electromaterials Science. Today, I will share with you our research work on 3D printed modular soft grippers for conformal grasping at the 2020 IEEE ASME International Conference on Advanced Intelligent Mechatronics. The research objective of this work was to develop a low-cost modular soft gripper for conformal grasping that incorporates 3D printable soft fingers with soft auxetic structures and compliant ribs. The design process started with modeling and designing the soft fingers along with their corresponding auxetic structures in a way that they can be 3D printed using a low-cost and open-source fused deposition modeling 3D printer. The 3D printing parameters were optimized in the slicing software in order to obtain airtight soft pneumatic bending fingers. In addition, in the same design process, we characterized the soft material used to print the fingers and their corresponding auxetic structures to assess its stress-strain behavior, and to develop a hyperelastic material model for use in finite element modeling. Finite element simulations were performed in order to predict and optimize the performance of the soft pneumatic fingers and to predict the contact behavior of the soft auxetic structures prior to their fabrication. Finally, we characterized the soft pneumatic fingers, the auxetic structures, and the gripper to quantify their performance. The soft fingers that drive the soft gripper and deliver the grip forces required to grasp various objects were designed to generate a bending motion upon their activation. A zigzag structure was chosen in the design process of the soft fingers to eliminate any contact between the walls of the adjacent chambers upon actuation, as shown in the figure on the right-hand side. A single finger is coupled with an auxetic and compliant structure as shown. The auxetic structure and its compliant ribs enhance the conformability of the gripper by increasing the contact area between the gripper and the grasped objects since they adapt to the shape of the objects being handled. A commercially available soft thermoplastic polyurethane or TPU known as Ninja Flex was used to 3D print the soft fingers and their corresponding auxetic structures simultaneously in one manufacturing step without requiring any post-processing and support materials using a fused deposition modeling 3D printer. Finite element simulations were performed on a soft pneumatic finger to predict its behavior and optimize its topology. The bending behavior of the actuator and its blocked force were accurately predicted in the FE simulations. The experimental bending angles and blocked forces of the finger at different input pressures agreed well with their corresponding finite element results, as shown in the figures on the right-hand side. Also, a series of designs were considered for the soft auxetic structure and simulated to enhance its deformation and behavior and to ensure that the fingers of the gripper can achieve conformal grasping with a wide variety of shapes. We performed highly nonlinear finite element simulations that included geometric, material, and contact nonlinearities in ANSYS Mechanical. Using FEM, we accurately predicted and optimized the performance of the fingers and their corresponding auxetic structures prior to their fabrication. This approach of using finite element modeling is very effective to rapidly and efficiently design soft actuators that meet certain design requirements and to save time, modeling, design, and fabrication resources. Here, we show the experimental bending deformation of the soft actuator along with its corresponding finite element deformation. Finite element simulations were also performed to assess the performance and predict the behavior of the auxetic structure when it comes into contact with different shapes upon activation of a single finger with positive pressure, as shown in the top figure on the right-hand side. For each object, the simulation was performed without including the auxetic structure and with the inclusion of the auxetic structure to show the difference in the behavior of the structure and the difference in the contact pressure and area. The FEM proved that the contact area increases with the inclusion of the auxetic structure, which adapts to the surface of the object in contact. Consequently, the contact pressure dramatically decreased as shown in the table on the bottom right-hand side. The contact pressure can be decreased by up to 8 times with the inclusion of the auxetic structure. Also, both the FEM and the experimental results proved that the auxetic structure included in each finger of the gripper is necessary to achieve conformability by dramatically increasing the contact area and consequently reducing the contact pressure. A gripper with a 2-finger configuration where the fingers are not equipped with an auxetic structure is not capable of holding the objects as shown in the top figure on the right-hand side. Although the fingers of the gripper are soft, they cannot adapt to the shape of the objects being grasped. The fingers curl as expected for such soft pneumatic actuators, and only their tips come into contact with the objects being grasped. However, a 2-finger configuration with an auxetic structure can hold the objects being grasped as shown in the bottom figure on the right-hand side. This result proves that conformability is necessary for grasping specific objects successfully. Here we show that the gripper with the 2-finger configuration, where the fingers are not equipped with an auxetic structure, is not capable of holding the objects. Here we show that the gripper with the 2-finger configuration, where the fingers are equipped with an auxetic structure, is capable of holding the objects being grasped except for the apple which slipped. The configuration of the highly conformal gripper can be easily modulated by changing the number of fingers attached to its base to tailor it for specific manipulation tasks as shown in the top figure on the right-hand side. Also, the gripper is highly customizable. The solid red circular base of the gripper contains 6 slots that are equally distributed where the number of pneumatic soft fingers can be modulated. Therefore, a wide variety of objects with different weights, shapes, sizes, textures, and stiffnesses can be grasped using the soft modular gripper as shown in the bottom figure on the right-hand side. Here we show that the soft gripper with a 3-finger configuration can grasp successfully the same objects, including the apple that slipped when it was grasped with the 2-finger configuration gripper. This result proves that modularity is necessary in addition to conformability for grasping specific objects successfully. Similarly, here we show that the gripper with a 4-finger configuration can grasp successfully the same objects. To conclude, we have developed a 3D printable soft modular gripper with monolithic soft bending fingers that incorporate soft auxetic structures for conformal grasping. A low-cost and open-source fused deposition modeling 3D printer and a commercially available soft material were used to fabricate the soft gripper. The behavior and performance of the soft fingers and their corresponding soft auxetic structures were accurately predicted and optimized using finite element modeling prior to their fabrication. Finally, the performance of the gripper was assessed in terms of grasping performance. Thank you for your time and attention. If you have any questions, please do not hesitate to reach out.